Purpose of the training, once again, specific to the topic is I'll be going over the one-step modeling and modification using the steel composite girder wizard, and also how to make modifications once you're done completing the modeling using the wizard, and how to review tabular graphical data for the 10th point locations for the bending moment and shear results, and also more beyond just the 10th point locations. How to define input parameters for design and load rating, and how to extract analysis, design, and load rating output, and how to generate those outputs in the automatic Excel and Microsoft Word format. The program version that I'll be using is 2015 version 2.2. For myself, the build date is June 12th. It's updated with the latest patch. You shouldn't have any problem doing the same procedure that I do if you have Civil 2015 version 2.1. However, if you have version 2015 v 1.1 or 1.3 or earlier versions such as 2014 or so, you might not be able to see the features that I'll be covering today. The license type that I have that can also do what I covered today are both the conventional or advanced types. No matter which version you have, you could do the same thing that I covered today. There's one limitations with the conventional type, with the construction stage analysis. I'll try to mention that portion later on too. I will be actively using the composite girder module today. So the composite girder module is composed of two parts, modeling wizard and design and load rating check. Currently, we have it for the steel composite girder bridges, but in the third quarter and the fourth quarter, we'll be implementing the same modeling wizard and design and load rating checks for the pre-stressed composite girder bridges too. And the training session for the pre-stressed composite bridge case, similar to what I'll be doing today, but for the pre-stressed composite topic, that will be held I'm not exactly sure, but as the 4th or the 5th session in September. The training, I'll be first covering the modeling. I'm going to first create a straight bridge using the wizard, and then I'm going to show how you can modify, and then I'm going to model curved bridges based on the basic information that I input already, and also modifying the model outside of wizard. Analysis, same contents I covered before, but I would like to mention I may not be covering step-by-step process that you can actually find in our load rating or design tutorial. Actually, in the GoToWebinar the tool set that you have, the lean, long GoToWebinar tool, at the bottom portion, you should be able to see an option that says handouts. So in the handouts, I currently uploaded two PDFs. One is for the design tutorial, and the other one is the load rating tutorial manual. So the contents that can be covered, like the step-by-step procedural information, I'm not going to focus too much on them, but rather I'm gonna try to show what are the spectrums of each options and functions, so that you actually get to know how to apply for your project, or if it is ever applicable for your case. And also I'll try to mention more about the things that are often missed or things that are frequently asked to our technical support team about the steel composite bridge structures. Now I'm going to open a program. And regarding how to check which version you have, you can go to this top portion, the top corner of the program. Then you're going to see an option called About MIDAS Civil. And when you click this, you're going to see the same information window with the version number and the build date. If you like to have this update, if you are a user already and would like to update your license, please let us know at ts@midasusr.com. Okay, starting from scratch. So besides all different modeling approaches, such as providing the node and element information manually, or importing the CAD DXF, or using the widget. Today I'll be covering the modeling approach using the widget because that's the best way that you can benefit from MIDAS Civil. So in the structure main menu, the steel composite bridge is located in the widget section right here. If you're not seeing the same option, it means that you have the older version of the program. If you do see the option, but if it's disabled, it means that you don't have the module. So the steel composite bridge widget is composed of 4 tabs: layout, section, load, and construction stage. So layout basically is to provide a basic layout information such as span information or the deck width or the modeling approach or how you like to reflect the substructure portion. Do you just want to model up to the bearing portion, or would you like to model the full substructure and superstructure? So that's the type of information that you define in the layout. In the section, you define further details about bracings and girder. What are the types of bracings you have? How can you space them? Or how can you, or what are the different girder sections that you have, and how you need to, and which location they're located. Loading, defining the basic dead load and life load in the conventional setting, in the pre-composite and post-composite setting. And construction stage, here just by clicking these options that are provided, you can automatically consider pre-composite state, post-composite state, and long-term composite state. Also, the flexibility of the widget allows you to define further sequence information, such as the deck pouring sequence and deck split construction information. Now, going over one by one. One more time, remember that today I'll be trying to focus on the parts that are often missed out by users, or like the common mistakes are made, where the common mistakes are made. Before I come to the widget, I would like to first define my properties, materials, and sections. You can also do it within the widget. So for whenever you find a section that's like a part that says section, we currently do not have any section or material. The list is currently blank. You can find the menu outside a widget under the properties main menu, or you can also click on this ... option, which you always see in MIDAS Civil everywhere. It will allow you to go to the interface where you can define the section information if you do not have something here, or if you need to define anything additional, or even correct or delete what you have. So let's work within the widget. First, I would like to define the materials. For the very new beginners, I'm just going to show how to define one material example. I'm going to define A709 50W as my girder for my steel material. And then I'd like to show you the import features. So when you click on the import, you can open up a dialog box in which you can import the materials or section information that you defined in the previous model. So in the previous model that I worked on before, I had a steel, concrete, and composite girder material. I'm just going to import them. And this is the part that a lot of common mistakes are made. So I imported not about the importing itself, but about this material type, SRC. So when you go to the type of design, you're going to see 4 different type of materials: steel, concrete, SRC, and user-defined. So steel, as it says, it's the regular steel. When you select this, you're going to see just the steel portion activated. If you select the concrete, no problem, it's one way too, you only see the concrete windows activated. Now, SRC, steel reinforced concrete. The terminologies may sound a little confusing, but just think of it as a material type in which you can combine the steel and concrete material. And the reason why I highlight on this is because this is the material type you need for the composite girder sections. Just remember, for if you are modeling, if you are using the composite type of section, aka grillage analysis approach, this SRC type of material, steel and concrete information together, this is the type of material that you need for the girder members. Just keep that in your mind. I'll come back to this when we go to the section. But in addition to the regular steel and concrete materials, I defined one additional that combines the steel A70950W and concrete C4500. They are combined into this composite girder material. And how I did it, I selected SRC type, so I can define both the steel and concrete material at the same time. Okay, keeping that in your mind. Now I'm also going to import the sections. How to define them one by one? You can easily find the information in our steel composite girder tutorials. I have some of them over here too in the in the go to webinar tool, the handout portion. If you're not seeing it, we'll also be mass mailing all the attendees today with all the manuals and model files used today. So I just imported the sections too. To go over what I have one composite type of section for the positive flexure area, and another composite type of section. You can, with the quick view window, you can take a look at what it is. An angle section, this will be used for all my bracing components. And pier cap will be modeled with just a rectangular beam. And P1 with the pier for the pier column. In connection to what I mentioned about the SRC type of material, this is what I meant. So when you add a section as a composite type, you're going to be able to input the slab and the girder information. Currently, the name section positive, the section type is steel I. You have freedom to define any other steel or pre-stressed composite sections. But for today's topic, steel composite I girder bridge, I've chosen steel I section. And the slab width, BC, is the center to center distance between the girders. And TC is the height of the deck. And HH is the hunch height. And here I put the girder information. You can refer to this window for what each symbols represent. And as a new feature added to 2015 version, you can also define the longitudinal stiffeners. And I'll also like to highlight on this portion. So in the material, the reason why we have the material portion within the section window is because in order to calculate the composite section property, we need to know about the concrete and the difference between the concrete and the steel material. So when you click on Show Calculation Results, you're going to be able to see the section properties for before composite state, after composite state, and long-term composite state. So in order to do this properly, program requires you to input the concrete and steel material type. So this is where it's been. And another frequently asked question is, I see the information here, but when I click it, it's blank. It's not taking my information. The answer is when you just say, when you just input the information and say OK and get out, it's going to change the information. But then when you click again, it's just going to be refreshed. So just because these windows are refreshed, it doesn't mean that these values are canceled out. So you don't have to worry about that. So by selecting the material for steel and concrete, we were able to calculate the ratio, the modulus of elasticity ratio, density ratio, and so on. And then this is another portion, defining multiple modulus of elasticity. So in MIDAS Civil, there are multiple ways to define to define the time dependency of the concrete. Let me open up one of the manuals that I also dropped in the handout section of the menu of the GoToWebinar tool panel. So we have three modeling approaches. One, as you see on my page, is to use the construction stage analysis and accurate time-dependent material functions. Before we get into that, let me provide you a quick overview. For the steel composite bridges, you have three ways to define the time dependency of the concrete. Method A is to do the construction stage analysis and use the creep shrinkage and compressive strength functions according to CBFIP or ACI and so on. The second way to do is to use the construction stage analysis and long-term modular ratio of 3n, which I was about to show you in the program window. And the third way is to simply define the composite action without the sequence analysis. And going over one by one, the method A, this is where you can get to each function that are needed for this type of setting. And to take a look at it with the interface, you'll get an idea that, one second. Yes, basically defining the time-dependent functions for creep shrinkage and compressive strength. The second method, this is what the wizard, this is the approach the wizard takes, and also I'll be taking and using for today's training. This is the most convenient, simplest way to handle the steel composite bridges, and also from the simplest like a one-span composite structure to long-span, multi-span structures. This methodology can handle any type of complexity or simplicity without any issue, and it will be the easiest for you to define as well, and also the approach the wizard takes. So for this one, the program will be defining sequences, stage 1, 2, 3, 4, 5, or so on. And then the program will be using the long-term modular ratio of 3n in order to reflect the time dependency of the concrete. And the third way is to simply define, do you see over here, the load cases for a pre-composite section. In this methodology, you can simply define, select the load cases that are applied in the pre-composite stage, and also you can reflect the creep condition using this boundary change assignment. Please refer to design tutorial PDF that I uploaded in the handout portion for any further information. But coming back to the program, so following the methodology B, I would like to use the construction stage analysis and the 3 modular ratio for reflecting the long-term property of the concrete. So based on my n value, I have my 3n. And then I'm going to say, okay, oh, another thing, I forgot to mention this portion. So You have this is also an additional feature implemented in 2015, V 2.1, 2.2. So this is to consider the warping effect. It's the seventh degree of freedom. You can benefit from this feature if you're working on any curved or skewed structure. If the warping on the web is one of your major concern, and if you will still like to take the grillage analysis approach, which cannot really consider the warping effect on the girder, you can still take the grillage analysis approach, model your girder and concrete with the beam element, but still reflect the warping effect on the girder by selecting this option. So this will be a very useful feature if you're working on a little more complex type of steel composite bridge. But if plate or solid analysis approach is too complicated and time inefficient for you. I'll cover more about the modeling analysis approach in the wizard. So we have our sections ready. This material and section information and the entire model, I'll be sharing that after the session to all the attendees today. I'm going to open a simple example since we don't want to spend too much time just seeing the inputs. Again, I'm going to try to focus more on the mistakes that are commonly made, or I'll also try to show more of the available capabilities, like the spectrum of the features that we are going over. So this example is a two straight span structure, two span straight. And after making a model with this example, I'll be coming back to the wizard to show how you can work with a curved structure or super elevated structure and other variables. So in the modeling type here, this is what I meant by if you want to do grillage analysis approach for a complex type of steel composite bridge, you can benefit from considering the warping. So this is also connected to that. So in MIDAS Civil Wizard, you can actually take multiple modeling approaches. If you do all frame, it's going to model your structure in the grillage analysis setting. All plate literally will be modeling your deck and girders using plate elements. And the third option is going to model just the deck as plate and girder as frame. And fourth option, the deck and web will be modeled using plate elements and flanges using the beam element. So depending on the cases you have, you need to choose proper modeling type. And also for the design, I'd like to mention here, all frame approach is available for design. For the plate, for the modeling approaches that involve plate elements are not compatible for design check. It's because when plate or solid elements are involved, the informations are not in the regular format that the program needs to perform the design check. But the benefit here is you can actually you can actually produce two identical structure with completely different modeling analysis approach. So you can actually do further comparison really easily just by using the wizard. I'll also try to show that part in the later too. And also a lot of the questions we get is, how do you know which modeling type is proper? So the answer, we have case studies from one of our longtime user, Daniel Baxter from Michael Baker International. He's actually done a case study regarding which modeling type is suitable or which modeling type produced him the closest result to the field data. I'll also try to share that information together with the materials that I covered today. And also another way to find it out is, as I said before, by creating two different model for the same structure with different modeling approach using this wizard. So for example, if you were to create all frame, you can just select all frame. Give me 1 second. So when I select all frame approach, as mentioned before, the grillage analysis approach is taken. When I look at the beam, everything is in the beam element type. No plate element here. But let's say you want to compare all frame analysis approach, grillage analysis approach, with, let's say, full plate analysis approach. Then based on the same information that you input before, you can simply open up, you can actually save the wizard file and you can open it up. Or when you just, within the same file, without closing the whole program, if you just go back to the composite bridge wizard, the information that you just put in will be staying there. So you can change some of the parameters and try out too. And in this model, as you can see, all the main superstructure components, the deck and the girder, are modeled using the plate type of element. So this way, you can quickly generate two different models for the same structure with different modeling type in a matter of a minute or so. Span information, deck width, and support skew angle. And another questions I get are where is this support skew angle referencing to, or where what is this layout offset, or where do you measure the radius, or and so on. So basically, for anything related to my bridge is curved or skewed, which line am I defining this information based on? For any of those questions, refer to this picture and look at this layout offset. So basically, the girder information, if you had a chance to look at the wizard, you will notice the girder information for girder 1, 2, 3, 4. No matter whether your structure is curved or skewed, have different length for each girder. No matter what the case be, you're going to notice that the end length for every girder is the same, meaning regardless your structure is skewed or curved, and like each girder line has different length, regardless of that, the girder length is indicated to be the same number in the section tab. If you noticed it and have a question, like, so where is it, why is it all uniform, should be different, the outer girder line should be longer, and so on, it's because those girder information and other information similar to that are defined based on the layout location. The layout offset. So the reference line is this one, and by default, the layout offset value is 0, meaning there's no distance offset, so the reference line by default is the centroid of the deck. So if you want to, let's say my deck width is about 36 feet, and let's say I want the reference line to be located at the end of the deck, you can actually put 18, so that now with the 18, your reference line is located at the outer edge of the bridge. The radius. For your structure, if your structure has uniform curvature radius, you can simply click on this number and just change the number here. But that's not a common case. Unless it's a perfect ramp structure, all the structures have varying radius, or you might need to reflect the vertical elevation change or super elevation change. In that case, I'm going to open up an example that has such condition. And all these wizard files and model files that I'll be using today will be handed out to all the attendees today. So please, this information will be provided to you. So if you have, let's say, plan vertical and or bank rotation, you can utilize our multi-curve option. So right now, I don't have any skew or radius, but once you select on this multi-curve option, this advanced button is enabled. And here you can define the plan curve information, vertical curve information, and bank rotation information. So combinations of these multiple curves and bank rotations, you can actually define it over here too. And these numbers are defined based on the coordinate and the station number. So it's very easy to interpret. And how to actually, if this doesn't seem familiar to you, I'll be also providing like an example model and manual for how to use this option. So you can refer to that too. I'm going to go back to the simple straight model that I had. Okay. And over here, this is actually where you can benefit a lot from our super and substructure portion. So basically, bearing type, this part I'd like to go over one by one. So the bearing type is literally to model just up to the superstructure. So this structure has the intermediate pier, but the next one doesn't have anything. This is the state that I'm referring to when I say bearing type. So no substructure, just up to the bearings. And there are two options, either support or elastic link. So the support option, these abutment and pier portions are disabled for manual editing. That means that this 10K, 1 to the 10 to the, I mean, 1 to the 10th kip per feet stiffness is applied for the connectivity to the abutment and to the pier. But when you select the elastic link, so the only difference between the support and elastic link is that when you do the support, this abutment stiffness and the pier stiffness are fixed with this 10th to the 10th value, which is very high and going to make it rigidly fixed. But elastic link portion here, you have freedom to modify the elastic link stiffness for the abutment and the pier. So here, if you need to, let's say, cancel the stiffness in the transverse direction or so, or if you only want to fix it in the longitude, the vertical direction, you can cancel kx or ky, or just ky, depending on what type of link that you need to model. And another option here is for different support. For example, my structure right now is made of two spans of 140 feet, right? And for here, I have three support sets: abutment 1, intermediate pier 1, and the other end support, abutment 2. So for each them, if you need to variate the elastic link stiffness value, the advanced is there for you. And this elastic link option is actually, you can actually refer to the guide for what it exactly means. So it's basically the gap between the pier cap and the bottom of the girder. So this can reflect the, literally from the bottom of the girder to the pier cap, it can be like the bearing height. And for the width substructure, and for the support, another thing to mention. So if you need to fix the transverse direction, if you want to choose at which support set you want to fix the transverse fixity, you can actually choose the two. And for the direction of the support, do you want it to be tangential to the curve, or do you want it to be radial, not following the curvature? You have an option. And when you use the tangential option, it's the support X, Y, Z locations. The node local axis will be rotated. There will be node local axis property applied to the support, so that the XYZ is not the global local node axis, but it's going to be the local node axis. So when you review the reactions and so on, this option can also affect your result. And tangential is most 90% of the time the setting that you want. following the direction along the girder lines. And with substructure, portion is relatively simpler. Elastic link is the same as I explained before. And for the pier portion, we can actually model the full intermediate pier and pier cap. So that's what this part is for. And here, if you want to model, let's say, if you want to model multiple columns, just like this picture, you can actually provide spacing number, and also you can differentiate the pier height for each stem. And for the pier, at the bottom of the pier, most times myself and also our user engineers, we mostly use the fixed support. Just use the pier support, make it fixed type, you know, like the simple support support component that we use, right? But in case you need to reflect the spring, the soil spring, you can actually choose the spring support option, and you can provide the horizontal, vertical stiffness value in the keeper, the length per and force per length unit. In the section portion, I won't go over step-by-step process, but I would like to mention that this angle type option and also the spacing, how you can handle the spacing, and a little more about the girder information. And actually before, so the bracing, you can actually different multiple type of bracing, X, V, or inverted V, make it inverted K, or whatever the case be. Freely selecting the top and bottom chord that you want to include for each bracing set. Once you define your bracing type, you can actually locate your bracings by providing the division number. So this division option will be how many divisions are there for the entire bridge length, or it can be varying, such as 12 at 10 or 5 at 15 and so on. So this is for the entire bridge length. Right now, 280 feet total for the current structure that I have. Distance here is to define the gap between the bracing by distance. This one too, you can also do it this way. If the distance isn't varying throughout the bridge length, you can actually input multiple different distances doing the way I do. But you just need to make sure, if you're doing the distance, you just need to make sure that the total sum of the distances are equal to the total bridge length. If you do the division per span, this will be useful if your spans are not uniformly long. So if you have 3 spans, let's say, and have longer middle span, and the bracing gaps are different between the middle spans and the 2 end spans, you can actually use this division per span option. And in case your bracings are different per each girder line, you can use this option. Let me show you a couple example. So I was able to model the lean-on bracing type like this. So I defined 2 types of bracing, one without the brace portions. And then I also defined on this full X-brace braces. And I located, they are spaced at different gap. So if your bridge is skewed and your structures, you know, like the bracings are actually starting at different part along the girder, you can actually utilize this option to apply the different bracing per girder. And also any alternative bracings, you can also reflect that. I did this one using the distance option. And also, most likely, you will have different bracing for the support. Then you can use this option And if you define any different type of bracing, let's say bracing 2 or bracing support, you can choose that option too. For the girder information, this is also the part that a lot of people get confused. One of the reasons is because when the structure is curved or skewed, pay attention to this end in feet. 140, right? So total bridge length is 280. And right now, I choose to apply the girder information symmetrically. And so it's only showing me up to 140, the half of 280. And here, notice 140. In girder 2, it's also 140. Girder 3, it's also 140. Girder 4 is also 140. And let me quickly apply some support skew angle. Let's say 30 degree, right? But the end is also the same, 140. So the total length of each girder line will never change. It's going to be the same as the total bridge length that are provided in the span information. But when your structure has different skew angle at different support or have curvature, the girder length may vary. It wouldn't matter because in the wizard setting, you're going to, for each girder line, you're going to define the girder section location about the reference line. So remember, currently our reference line is with the 0 offset located at the centroid of the deck. So regarding the location on each girder, you can actually draw the perpendicular line to the centroid of the deck. And from here, let's say from this point, you're not going to input the distance from here to here. You're actually going to input the distance from here to here. From the outer or the inner girder line and draw a perpendicular line to the centroid of the deck. And this number from the beginning of the main centroid of the centroid to whatever the location be, that's actually the number that you want to apply over here. So how to determine the locations for outer or inner girders about this reference line? It's about the perpendicular line from the outer girders to the center line. And about the setting itself, if the wizard is confusing or if you need to know more in the graphical format, please feel free to utilize our guide option here. Okay. And also, this is another major portion that I like to highlight on. So basically, this option is really valuable, 5 stars for this one. So usual FEA program. So unless you you divide your like a span into 10 numbers, or unless you actually purposely locate your node at the 10th point locations, it's really difficult to manage the 10th point location for in FEA program. And it's even more so if you are working on a little more complex types. But with this option, you can actually have the program do that process automatically for you. And this is the part where you can benefit a lot in reviewing the result and design and load rating result. So I'll be going over the result about the 10th points. And not to give you any wrong idea, if this doesn't really limit you for reviewing any other points, such as like the contra flexure point, that's not exactly the 10th point. Yeah, there's no limitation. It's just that in addition to reviewing the result at any location, you also have an option to review the result at the 10th point locations. And also the locations of the splice girder can be mentioned over here. Not going to do it for now. Actually, for the pre-stressed composite bridge wizard that will be released next month, yes, splice girder modeling and design are one of the most frequently asked questions. Yes, it will be there too. If you have a stringer, select the stringer option by default and select the section, the I sections. And by default, the stringers will be located between at the center between the girders by default. So you don't have an option here. If you want to modify the location of the stringer, you will need to do it outside of wizard. Loading portion, I don't really want to cover because this is a very simple step-by-step process. But one more thing to mention. So in MIDAS, we actually implemented a lot of DOT vehicles. If you haven't upgraded your program, actually in the 2015 V 2.1 and 2.2, you should be able to see a list of the vehicles. And besides the AASHTO, LRFD, and the old standard load and the legal and permit trucks, you will also see the DOT loadings. So please take advantage of this load database. Let me quickly define my vehicles. I'm just going to define the design truck and tandem loads. Okay. And this construction stage portion. So here, let me reset my setting. You have multiple options. Think about it in a simple way. When you click on the construction stage option, refer to the table that changes as you click on each different feature. So when you click on the construction stage, it is going to consider stages with different things happening in each stage. So by default, this is actually the fixed template. You don't have freedom to modify this. You only have an option to change the duration of each step. So by default, if you choose to model the intermediate pier and pier cap, you have the first stage by default, the substructure will be activated, substructure erection. And in terms of loading, the self-weight is activated. So once the self-weight is activated, it's going to stay there. And as additional, let's say, girder or bracings are installed in the later stages, the self-weight are calculated based on the section and material property. So once the self-weight is activated, you don't need to deactivate or activate again for other part of the structure. By default, self-weight function will be calculating the weight of each component according to its section and material property. So once you activate it, it stays there. And as other part of the structures are activated, automatically their material and section will be counted toward a self-weight calculation. In stage 2, the girder and bracings are installed. In this wizard setting, the girder installation sequence or bracing installation sequences are not considered. If you would like to consider them, you can do it outside of wizard. I'll also cover the portion once we're done covering the wizard. And the stage 3, in the first stage, if you do not want to consider the deck pouring sequence, it's going to pour the deck to the entire in the entire deck cover. But if you want to, so in the 3.1, just the loadings are applied. So wet concrete is there, but as a wet concrete without any stiffness, without any strength, it's only going to impose the weight on the bare steel members. And in 3.2, the deck members, as the structural, as the actual members, they will be activated, therefore having the full strength and stiffness in the 3.2 stage. And in the 4th, by default, the after composite load is activated. So barrier or additional wearing loads will be applied in the 4th stage. And before getting to long term, let me just mention about the deck pouring sequence. So when you click on deck pouring sequence, did you notice the number of 3 stages change? It was just 3132. Once you click it, it's 3132, 3334. And you'll see that D1, D3, D2 are activated in sequence. And the reason what is D1, D2, or D3, you can actually find further information in the deck split construction. So depending on your state regulation or the type of structure, the complexity that you need to consider in the actual model may vary too. So from simple, just considering pre-composite or post-composite, to actually considering the deck pouring sequence, you can handle them in the wizard. And what is D1, D2? You can actually refer to this picture here. D1, D3, if for our case, we only have 2 spans. So only up to here, right? And D4 is not there because here the negative flexure don't occur. So we only have D1, D3 in the positive flexure zone and D2 in the support area. And how do we know how much of the length each D1, D3, or D2 are covering? You can actually specify that information here in the advanced, or actually the negative moment zone length is what it is. So it's currently 35, right? It means 35 from the support to the end of D2, and also another 35 to the other end of D2. So total 70 feet. But if you want to, if this is too big or if it's not symmetric about the support, you can actually manage them over here. Okay. And this is also the important part. So right now, the modeling approach that I have taken is to use the steel composite stage and the 3M modular ratio, right? Notice when I click on this button is enabled, and then I can click on this, and it's giving me 2 options, creep 1 and creep 2. What are creep 1 and creep 2? Let me cover that portion in a second. But basically, in order to consider the 3M modular ratio, you will need to check on this option, go into this long-term boundary group, check on creep 1, creep 2, and say OK. So that way, the 3M modular ratio is considered in the 5th stage. And what were the creep 1 and creep 2? I'll be mentioning that in briefly, in shortly. And reinforcement, if you want to define the reinforcement information, you can also do it outside of wizard too. You just have an additional you can actually do it here, or you can do it outside of wizard, or you can do it right before the design check too. You can refer to the design tutorial for more about the reinforcement. And then let me just save it as. I'll also like to show you how to utilize the save and open option here. Let me save it with our date-to-date, July 15th, 2015, elite training session 1. So when I say open, if you want to modify the information that you input today, or if you want to continue working on the wizard information that you used before, you can always click open here and bring this wizard file information. And once you do, you don't have to re-input all over again. It's just going to be there for you, saving time to from the reworking on it. Okay. So I created my structure. As you notice, remember I put the 30-degree support skew angle, and it's still the straight structure. I mean, let me change some of the visual settings. If you are curious about what I'm doing right now, you can actually refer to the record, or we'll provide you the FAQ manual. But basically, I changed my color setting, so different sections have different color applied to it. Right? Okay. And remember the creep, the long-term property. So basically, when you remember this portion, click using this option, multiple modulus of elasticity. So basically, when you click on this option and when you input some value to creep or shrinkage, it's going to generate section stiffness scale factor. You can see it over here. So the section stiffness scale factor information is created for the first section positive. Notice the names are the same, section positive, and section negative. And the reason why the group name is creep 1 and creep 2 is because the modular ratio is input for the creep property. And when let me show you what they are exactly. So when you go to section positive and about the stiffness, you can actually see the ratio. And this ratio, you will notice when you click on it, it's applied for the after composite section. And also, you're going to see different ratio applied for the area or moment of inertia and so on. So this is to basically scale down, reflecting the increased modular ratio so that the decreased concrete strength is reflected with the section scale factor function. And it's applied for the concrete portion too with this option after. So that's what the creep 1 and creep 2 are about, and that's how MIDAS considers the 3M modular ratio. And another hint here is, another frequently asked question is that, can you reflect the steel deterioration or corrosion in MIDAS? Common questions for the engineers that are working on the load rating projects. Again, civil can cover the load rating too. So in order to reflect the deterioration or corrosion, you can also utilize this section stiffness scale factor. So as much as the corrosion is affecting the section strength, you can actually use this scale factor to bring down the strength of this, the full stiffness of the section. Okay. And let me show you one more example of the wizard. So before I had a straight structure, but this time I would like to model this as like a ramp. And also this time I would like to vary the bracing distance. It's straight distances, total 280 feet. Give me 1 second. So at this time, I provided the curvature radius information, and also I differentiated the girder, the bracing here. Let me turn off my 3D view and also go to the top view. And here I'm going to select the truss so that you can actually see the truss highlighted. Let me give me 1 second, change the color setting so it's easier to notice. So notice how the bracings are starting at different location, and it's varying between the girder lines. The starting point of the bracing is different and all that. So this type of setting can be reflected, and also the curvature and the straight and skewness. And also here, let me show you how you can change. Let's say one of the common misconception is that civil is only for the existing structure projects. I call it misconception. It's because the way conventional design programs are working and the way MIDAS is working is a little different. So if you have preliminary design, so basically you're gonna need some preliminary information. But once you have it, you can quickly generate your model using the wizard and run the analysis, do a real quick design check, which I'll be showing shortly. But then always, there may be modifications, right? Rather minor, regardless it is minor modification or major modification, you can actually handle them all, either inside a wizard or outside a wizard. So let's say you were planning to model just the 4 girder composite bridge. Then you can say 4 number of girders and apply, but let's say the number of girder changed. You need to say 5 or anything else and change the information. So you can do it within the wizard too, as you just saw. Or you can also do it outside of wizard too. Let me redo the wizard work. And here, let me show you how you can change, let's say, section. Let's say you tried out particular sections and it didn't work. So you need to make it more conservative, let's say. So right now, I applied the color setting to be different for different girder and pier cap and so on. So you notice that this support area and non-support area, they have different color applied to the girder, right? It means that 2 different section properties are applied to the entire girder lines. And when I double click in the trim menu, I can tell what they are. But let's say here, I need an additional girder section. I need something between. I actually need something more conservative for the support area. Then you can actually simply right click in the section, or you can go to the properties, go to the section properties, and you can actually copy what you had already. And here you can modify the information. Let's say the thickness of the web needs to get larger. Let's say it's going up to 0.75. 0.75. And let's say also the bottom flange needs to get thicker. Actually, let me make it drastic so the changes are very noticeable. Here, let's say originally this negative section was applied to with the original 0.05 feet and 0.2 feet thickness for the web and flange. But let's say I need to change it to something else. All I need to do is select those sections using the section property or material ID or using the selection tools, whatever the case be, and drag and drop the new property that you want to apply to. So this is one way of modifying, and also you don't always have to define something new and apply it again. You can simply modify within the wizard too, right? And let's say if it's not exactly the whole group of elements that this section is applied to, let's say it's a combination of here, these sections and these sections, right? In that case, I can actually activate them only. So using the section property, you can not only double click and select them, but you can also activate a part of it by right clicking here and choosing active, right? And let's say it's an irregular portion, like the transitional portion here. Then needs the new section property. Same way. So now I have multiple sections. So if you're working on a preliminary design project, let's say you only start with like one approximate girder section and concrete deck, you can actually always come back and easily modify and run design and do the design check. And based on the design check summary table, you'll be able to easily figure out like how to modify your girder or the concrete portions. Okay. I won't be covering too much about moving load analysis, but now let me move on to the post-processing portions. Actually, before we do, let's quickly review the stage settings. Stage 1, Stage 2, Stage 3.1, 3.2, and 4, and so on. Okay. I'm gonna try to conclude the session around 2:40. So for the remaining 20 minutes, we can have a Q&A session. Or if there aren't many questions, I'll be closing my trainings around 2:30 to 2:40. So this model, I actually ran the analysis for the sake of time. And this one, we can see in the stage 1, the substructure is erected. Stage 2, the girders are installed. 3.1, the wet concrete loading is poured. So basically, how do you find out which loading is applied on each stage, right? So when you are in the base stage, everything is there. Every loading you applied is there. Every support you applied is there. Every section is there. But when you start changing your stage, it's going to show different things in the workstream menu. It may be less, it may be more. Most likely it will be less. Stage 2, three one, 3.2. Notice the changes in the picture, but also notice the changes in the stream menu. 1, 2, 3. So different component of the structures are activated in different stage. And it's actually following the template in the wizard. And here I actually forgot to mention, if you want to reflect girder installation sequence, you can actually right now I have girder group, and all the girder elements are included in the girder group. But if you want to sequence your girder installation, let's say you want to install the first the inner girders and then the exterior girders, then you can actually create girder 1 and girder 2 and activate them in different stage. More about the construction stage also we'll be covering more specifically in another type of section. So today I'm going to try focused on just reviewing, extracting the moment shear diagram and design and load rating result. Okay. So once you're done executing the wizard, in the group tab, you're going to notice a lot of things are listed. And these are all automatically created by the wizard. And the things that you need to notice are this 10th point girders, 10th point girder 1I, 10th point girder 1J, 10th point girder 2I, and 10th point girder 2J, 10th point girder 3I, and so on. So what they are exactly. So the 10th point locations are difficult to find in FEA program. You either have to consider that in the very beginning modeling approach, when you start the modeling. So you have to make sure node, let's say 1, 20, 30, 40, 50, 60, 70, 80, and 90, and 100 are located at the 10th point length, right? But if in case it's curved and skewed, no worries with the wizard, it will be doing that for you. And this 10th point girder 1I, for example, so what it means, why do we have the group ending with I and J, right? So basically this 1I means this is for the girder 1, this is for girder 2, this is for girder 3, this is for girder 4, right? But girder 1I means the I node of the elements included here, they are the ones located at the 10th point. So each element has I and J node, right? Let me turn on my element direction. Okay. And I'm also going to leave just the girders so we can clear our view. And selecting the girder 1. So if you remember, our bridge, this one is 140. So remember, this structure had total 280 feet length and 140 feet bridge span each. And here, the I node of each element, the starting node is where the 10th points are. So each group will be containing different group of elements. But the I node of it, so if you look at the direction here, it's going from 3 to 28, right? And the 3, the starting node is the I node, and 28, the end node is the J node. And for here too, 760 and 54 are the nodes for the second element. This is the I node and this is the J node. Give me 1 second. Let me increase my node number. Never mind. Oh, yeah. Give me 1 second. Okay. So do you notice the node numbers? 376, 761, and 762 are the locations of the 10th point. And how can I prove it? Open the query dialog box, and then let's click on 3. Notice the 3 is at 0, 0, 0, 761. It's at 14 feet away. The distance between the first one and the second one is 14. And 761 is at 14 again, from the 760 to 761. 762, again, it's at 14 feet away from the one that I clicked before. It's like this throughout all along. So this way you'll notice there are the 10th points. Okay. I'm going to turn off the local direction. Okay. And then here, when you review the result, we have 4 formats. One is the diagram, which are used most frequently. And the other one is the tabular result, also used most frequently. And the fourth is the text output. And the fifth is a combination of all of them. So now I'm going to show you each one by one. So in the diagram format, I believe this is something very common and familiar to all of our user attendees today. So I'm not going to stress much on this. But rather, this 10th point portion is something new. So let me go get to that portion. If you are relatively new to our program, or if you're not familiar with the basic diagram portions, please, you can reach me, myself, or our MIDAS soft. You can actually reach me at, or you can also reach me directly at angelakim@midastudio.com. But let me get to the 10th point portion. So basically, by clicking this, you can get to the tabular result. Or we have our main menu here, result tables, beam, and forces. It's going to be the same thing. It's just that the program has the default location for the tables, but you also have an option to get to the shortcut. And here, this is often disregarded, easily neglected portion of the program. but it's something that can really help you. Instead of spending a lot of time again in the Excel, you can make a lot of things very easy through this activation dialog box. So basically the bottom point is that if you want to review just for, let's say, the bracings, you can easily filter that using the section type. Or you can also filter using the material type. Notice the number don't change because they are about the same bracing members. So this way, select the load case or combination and say OK, right? This isn't about the 10th point, this is the regular way. But basically, just now, I created the table for the bracings. But we are curious about the 10th points here. So 10th points locations can be found in the structure group. Structure group. And going down, you're going to see different groups to substructure, capping, meaning the pier cap, bracings, girder, and then the dummy beams, the transverse dummy beams, and then we have the 10th point girder groups showing up. And these, let me try 10th point girder 1I. And remember, it was the I node of the group of elements, right? So right now, by default, part I and part J are both selected, but I'm going to uncheck on part J. Because remember, this 10th point girder 1I, the 10th points are actually the I node of the group of elements that are selected. So when I select 10th point girder 1I, I only need to check on part I. And let's say I want to review about 10th point girder 1J. I need to uncheck part I and check on part J. And let me show you what they are like. So now I created the 10th point result for the first girder line. Let me close the message window and zoom into this table more. Let me count them down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the 10th point locations. Let me graph it. Just the moment graphs. So if you want to do a quick graphing, or if you want to graph a lot of them, let's say all the moment all together, you can select them. I selected multiple columns using the control key. And you can click on show graph. You can label them if you want. Say OK. So very noticeable which one is the major bending moment, right? And which ones are the minor axis bendings, moments. But do you notice here that, yeah, so graphing like this. And one thing I would like to mention here, this is something that are commonly missed by a lot of users. Let me refresh my view a bit. Okay. So remember, 10th point girder 1I and 10th point girder 1J, right? But do you notice how the 10th points are not really covering to the very end? So 1I isn't covering this end, 1J isn't covering the other end. And the reason is because this group is about I node, right? By having this group about I node, there's no way to select the endpoint here. This isn't an I node of anything. So there's no way we can figure out, we can select, we can get the result according to this. What you have to do, what I do is, let's say I extract the result about one I group, right? Selecting part I, selecting 10th point girder 1I, replacing the number. Okay. So here. Let me copy them, paste it to Excel. Right? But then this one isn't including this end. So what I have to do is I have to bring the active records once again. Go to structure group. This time I'm going to select 1J, replace, but I'm not interested in anything before. I'm only interested in the last one. So leaving only the 503. So this is the last portion of the information that we need. And if you look at it, element 305 is located over here. Oh, 503. So this way now the extraction for the full 10th point is now completed. $21 points, right? Okay. So this is how you can extract the shear or bending moment about the 10th points. About the second girder, third girder, it's only a matter of choosing which girder you like. And here I would like to introduce you that part, how to compile them all together, right? So let's say in the model view, I would like to draw like an overall. This part, if you have attended our webinar, you probably know about this pretty well. If you haven't, so I'm just going to introduce it very briefly. But basically, for any diagram or any table or any text output, you can always save them into the dynamic report image, text, or table. Always right-click in the model view and go to the bottom, dynamic report image. And I'm going to say load combination. Actually, this isn't the load combination 1. Let me get to the load combination 1. Going to save it as load combination 1, bending moment, and save it. And this time, I want to go to the 10th point locations. And I'll also like to save this into the table, dynamic report table, right? When I click it, it's giving me options to include, check on which part I want to take to the final table. Let's say if I'm not really interested in, anything besides the bending moment and shear, I can uncheck on the rest of them and just select the element and the load combination and say OK. Let me do one more thing, the text format. So here I'm going to get to the text output. Here it's telling me to add or create a load case. I'm going to say unselect but select only one. Okay. About the load combination 1, load set 1, I'm going to say next. And then it's telling me if I want element output, beam output, stress output, I'm going to select them all. And next. About displacement and reaction 2. And then. So this way, you can also create the output in the text format, whichever case it is. Feel free to, don't feel limited with the type of output provided. Okay. And about how to compile them, let's go to the Tools main menu. Here, I'd like to go to the dynamic report. You can either open an existing document or you can open something new. Let me actually open something I created before. Give me 1 second. So this report that you are about to see, this report is actually created based on a similar model using the same feature. So these images are inputted using this feature. What I mean by this feature, let me cover them right now. So let me just close this real quick and let me open a new one. So remember we saved the bending moment overview diagram and we also saved the 10th point table, right? So when you go to the report tab of the tree menu, you're gonna see four things: images, table, chart, and text. So basically chart, if you save anything like this, basically any of these charts, you can actually save them here. So images, when you open them, you're going to see two parts: user-defined images and image files. User-defined images are the ones that you saved. So when you drag and drop, it's actually put to the Word document like this. Table 2, I saved my 10th point table. I can find that in the user-defined table. And special tables are the ones that are there by default. B4s. And also special table, summary of the sections or the section, the reinforcement and so on. You can drag and drop. And there's no need to work on this again once you make any changes. So let's say remember I just drag and drop the section positive section summary, right? But then let's say I want to change the information. Going back to the original modeling input, let's say I'm changing some of the inputs. Let's say I change this to 5, right? Or let me actually make some drastic changes. So the changes here can be very visible. Okay. Okay. I don't want to I don't want to delete my analysis result. But basically, once you modify, you don't have to delete and drag and drop once again. All you need to do is just use this regeneration option, and you can actually check on the options. I mean the data that you want to refresh, and say regenerate. Right? Okay. Not going to stay on that for too long. So basically, that's how you can review about the 10th points. Now let me cover the design and load rating. So starting with the design, for the steel and reinforced concrete, design optimization is available. It's actually a very simple process for each stem. If you would like to know more about the steel and RC design, they're very simple and can be followed through. There's only 2-3 steps that you need to go through. Please let us know. You can actually find the design tutorial in over here, the handout portion too. So what I mean by the handout is that when you look at the GoToWebinar tool, you're gonna see an option like this. And there I already put 2 manuals, design tutorial and load rating tutorial. So in the design tutorial, you can not only find the composite design, but you can also find the steel design for the bracings and RC design for the pier and column. So please refer to them. The RC concrete and the bracing design checks and optimization are relatively simple. So let me go straight to the composite design, which is more new and also more complex. So basically, you will first select the design code. We currently provide AASHTO LRFD 12, 07, and Eurocode and Korean code. And once you choose your code, it's going to provide you the different menu set. Design menus are also very straightforward. Basically, stick to this idea. If you want to do the design check, just go through the menus 1 through the end. And that's it. Some of them you do not need, some of them you do need. But you can actually refer to the design guide manual for more about how to handle each interface. But here, let me focus on some of the questions that are raised more frequently. So basically, design parameters, it's about just making sure the design input parameters are correct and you want to consider. And design materials, here, the reason why we have this portion is because, and this is actually related to the SRC portion I mentioned. So remember I talked about you in the beginning, for the all frame analysis, grillage analysis approach, you must use SRC material type, right? But it's not the case if you are doing any plate modeling, like if the plate is involved for the deck or the entire girder or just for the web session, whatever the case be, if it's no longer just one beam, you do not have to worry about it. But in order to get to the design portion, you need the grillage analysis approach. And here, for the material, you have steel, concrete, main rebar, and sub rebar information. So for the regular steel, for the bracing, see we don't have the concrete material. This is why we need to have the SRC material that contains the both steel and concrete information. And here, let's say if you need to modify this for any reason, you can, let's say right now the specified compressive strength is 648 kPa square. But if you need to modify them, you can say none and change the specified compressive strength. Let me stick to what I had. And also rebar information. And also for steel, the yield strength or so are already there. But if you want to define them manually, you can choose none. And here we also have an option for hybrid factor. So if your girder is hybrid, you can actually use this option to variate your girder and the flange material. Okay. Load combination type, just please refer to the tutorial manual. And transfer stiffener. So basically, stiffeners, they are not defined together with the longitudinal stiffener. If you remember, when we defined the section, the longitudinal stiffeners are here, right? But the reason why transverse stiffeners is separated and in design is because the stiffener information, it doesn't really go by per type. It rather goes by the look, throughout. It's not strictly relevant to the type of section. And also because the transverse stiffener is not a section property, it's rather related to geometry of the structure. They are done separately over here. And unbraced length, okay, also, if you have different unbraced length, you can also reflect them. So let's say this case, we actually have uniform brace spacing. But let's say our brace spacing isn't really regular. Let's say it's different between the first span and the second span. Then if that's the case, you can select part of the girders, let's say just the span 1. And let's say the unbraced length is about 10 feet for the first one, right? Then you can choose the girders for the first span only and say 10 feet and apply. But if you want to choose the second one and apply different unbraced length, let's say 20, you can also do that too. So this way, you're not stuck to one brace length information. You can vary it as much as needed. And this is actually also very commonly asked questions. So the design position. So here, if you look at the menu, you're going to see two things, design position and position for design output. So design position is basically to let the program know where to check the design. So most likely for the design position, you want to select the entire girder line, and you probably want to check about both ends of elements. So here and here, for example, and for this element, and apply, right? But also here, if you don't really want to check the design about every portion, let's say it's a huge project, let's say you're done with the other parts, you are only about to examine a certain part of the structure, right? If that's the case, you don't really have to include everything for the design position. You can actually select a part of the structure and apply the design position. And here, don't get me wrong, checking the design portion at a part of the model, it doesn't mean the rest parts are considered there. It doesn't mean the rest portions are not structurally there. It's everything is there. It's just a matter of checking the design at which location. So if you have a huge model, you probably want to just trim down the location, just so when you review the result, you're not just swimming through thousands of sheets and columns and cells. But if you're working on like a regular, let's say for any type of structure actually, including all design position will be, it's just fine. You can do that way. But the thing is about the design position for design output. So design position is simple. So the program will run the analysis very fast compared to any other program. And checking the design is actually even quicker because it's just an iterative like calculation process that's very easy to handle for the program, right? But the position for design output, do you notice the little tiny Excel mark right here? Position for design output, right? So this one means I'm not sure if you are aware of this, but you actually have three ways to review the result: table, diagram, and report. And when you review about the report, that's what we mean by position for design output, right? So Excel design report, let me show you a quick example so that you get an idea of what you're doing for the output position. So basically the design output, you're going to be able to extract this detailed report about the location that you select. For example, this one has 445i, and this type of detailed design check procedures and result will be presented. And about the location 445i, let's take a look at what it means, right? 445 and I. So if you notice, it's the member right over here. And I node, right? Remember the direction of the element? Direction is going from left to the right, making this one the I node. And the reason why I've chosen 445i, so not the element, it's just this location, what the Excel is referring to. So this 445i isn't about the segment, it's about that location. And the reason why I selected that is because this is where the maximum positive moment occurs for the first strength limit state load combination. And how do you check it? There are multiple ways. So here for the design output, since this type of detailed report is created, you don't really want to overwhelm the program with thousands of data points, right? It takes about a minute or 2 minutes for creating each location data like this. So if you want to, don't select everything and select I and J and apply, because then we have about like hundreds of data points to create this Excel sheet about, and it's going to freeze your computer for a little while. So unless you want to sit your computer overnight and have the program do all the work while you're not actively using the program, please eliminate the data point to some manageable size. Let's say like 3 points. This report will take about 3 minutes for my computer. I have pretty good computer. And if you have about, let's say, if you can have it sit for like 30 minutes, it could probably manage about 20 data points. But it's very important to trim down what you review for too. I mean, it's great to extract the report, but then if you have the report for like hundreds of points, when are you gonna have time to review all of them, right? So now let me actually guide you through how to know which point to actually examine more thoroughly, and how to utilize our analysis result and design result feed functions to help you figure out where to focus on. So going to the result, you can actually identify that based on, let's say, bending moment diagram. So for the first load combination, I checked on the legend too so that I can see the summary of this bending diagram. Without this, I'll barely know what it means since it's just full of colors and members. So it's telling me the value for each color tab, and also the load combination and the maximum location and the minimum location. And if you want, remember, you can always save it into the dynamic report image and drag and drop in this report feature, remember? And here, it's telling me the 667 is where the maximum positive moment is occurring, right over here. And it's also telling me location 614 is where the minimum bending moment is occurring. So this way, you can actually find out where is the critical point based on the bending diagram. Or you can also, let's say you also need to know about where the contraflexure point is. You can also include it into your detailed Excel report too. So whatever the case be, but reviewing the analysis result is one way to do that. Also, if you want to stay within the design check, you can do that too. So I defined my span information. So going to structure, going to composite bridge, you can see that I defined my spans. Span left 1, left 2. You can name them more professionally. Span 1, girder line 1, or span 2, girder line 2, and so on. So basically, I have different group of girders per span. And when I go to the design check, I have 3 ways to review. Remember, diagram, table, and report. Report is actually the last thing you want to review. Before getting to the report, unless you're interested in knowing how to modify your design right away, you first want to kind of look at the diagram for an overview. I mean, if you are confident that your design is very conservative, just like what I have right now, you can just go straight to the table. But this diagram portion will provide you a really good overview of if everything is okay. Capacity versus demand graph, that was. And once you're done checking, doing a real quick check with the diagram, you can now get to the tables. Go to span checking. So do you notice how we have the different layers of tables? So there's bar between span checking and total checking, and there's also a bar between this group of tables and shear conductor and longitudinal stiffeners. So we have different level of tables, and the level is divided by the detail level of each type. So span checking, as you can kind of guess from the name of the table, this is the checking data about like a summary data for each span. So span checking table, remember I had multiple spans named left 1 through 4, right 1 through 4, right? If you have girder 1, span 1, or girder 1, girder 2, span 2, whatever the case be, it's going to be shown over here. The reason why we have positive flexure and negative flexure is because we are checking both for the positive flexure and negative flexure about each span, about the flexural resistance check. So going to the right, starting from the strength limit state, you can actually see a summary for each span about each limit state check. Let me actually narrow the columns. Actually, MIDAS result tables are very flexible. You can increase the column, decrease the column, and you probably noticed you can freely zoom in and out. Right now, you can see, but I am currently using the wheel button. I'm rolling it up and down. And you can also, you need to press onto the control key to do this zoom function. So not only the model view, but also table. Yeah, you can actually make it more comfortable for your eyes. So strength limit state, flexural resistance. Strength limit state, shear resistance. Service limit state, fatigue limit state, constructability, flexural resistance check, shear resistance check. And here, the shear connector and the longitudinal stiffener checks are, they follow. And the reason why the bottom lines are red is because you could probably get it intuitively, but it's because somewhere along the summary line, the checking has failed. So if one thing fails, the whole summary table is colored with the red for that span, so you don't really miss it out. If it's NG and just black color, it will be very easy to miss it out. It's all the way in the end. But by red highlighting the entire row, it let you know, give you the warning sign. So this is the summary. And by looking at each line, for example, let's just take a look at the left one, right? It's telling me element 668 and J node is where the critical location of the check occurs for the negative flexure. The load combination, the critical load combination for this case is the first load combination. Same case for all other strength limit state check. And this is the ratio and the result of the check. Same goes for the strength limit state shear check. Element 652 I node is where the thing is occurring. And let me actually tile this horizontally so that we can see two things together. Let me close my secondary menu to give ourselves more room. So here, let's take a look at where 688 is. 688, negative flexure, it sounds all right. It seems to be right around the support, right? The J end, okay, that's exactly where the support is located. And 667 for the positive flexure. It's right in the center of the first girder line center. So this way, this table let you know where you need to check the detail report for, right? So this is one way to know. By reviewing the summary table, it's going to let you know the most critical location and the ratio, the check result, and the end, is it okay or not? If you want to go straight to the report, you can do that too. But in case if it's not great, if it's not good, you need to iterate the design check process. You probably want to check more detail, like a force table and so on, right? The total checking is actually the summary table for each element. So the same columns, same shear limit, strength limit, flexure, shear, strength, service limit, and so on. Same columns, but about every location on the girder is the total checking. And the rest of them, strength limit state check, about flexural resistance, service limit state, fatigue, they are specific to each limit state. So if you look at it, this table no longer has the information about service limit state or constructability check. You're only seeing it for the strength limit state check. And you see the force results, summaries. So that's how you can determine where to extract the design report. And we are actually running out of time. I'm sorry to rush this part, but for the rating 2, we already have the tutorial manual. But I would like to go over this one part that we very often get questions. And so it's the load rating. Moving on to the load rating tab, you can also choose the code. Currently, we have LRFR11. It's actually indicating LRFR11. I'll make sure the terms are fixed for the next version. But basically, LRFR is available. If you need to do the LFD approach, no worries. We actually, it's not there by default, but you can actually do a workaround by flattening the load factors and so on. And we have a tutorial manual for the two, very simple. It's just about one part of the rating. So you can also do the workaround for the LFD approach, for your information. And the part that a lot of people get confused, so between the design input and the load rating input, a lot of things are very similar, very identical. If you remember, if you didn't have chance to get familiar with the design portion, let me tell you, longitudinal reinforcements sounds really familiar. Transverse stiffener, also familiar. Unbraced length, also familiar. Fatigue parameters, curved bridge info, they are all something that we already had in the design portion. So once you did it for design, let's say if you are doing the load rating check after the design check, you don't have to worry about these inputs. Only if you haven't done design and just jumping to the rating, then this will be something new to you. But once you define in the rating portion or the design portion, they are going to stay there for both the design and the rating check. And some of the rating specific functions are such as rating parameters, rating group setting, and defining rating case. And it's actually, this is where the factor definitions come in very critical. Give me 1 second. So here I'd like to cover a couple things. So system factors right here. In the group setting, you also have condition factor. So right now, if you notice, condition factor 1 is applied to the Girder group. So what is Girder group? It's the structure group that's including the entire structure. But here, if you actually want to distinguish the condition factor for different part of the structure, you can actually create different structure group. And let's say I have Girder 1 for the first span and Girder 2 for the second span. In that case, you're going to have Girder 1 and Girder 2. And for different groups, you can actually apply different factor. And the last thing I want to mention, and also very frequently asked about, is the defining rating cases. So here, so basically, when you just look at it, it seems like, so one of the very common mistakes is that people usually forget to look into this portion. And they often leave it out, like there's nothing. But what this is doing is, for the load rating, let me real quick. So this is also the design guide manual. It will also be handed out to the attendees today. So attending our seminars, you can actually benefit from receiving the collective information of our the training materials. So basically for the rating, especially for the LRFR approach, you need the rating factors. For the DC, we have the factor for DC. For DW, we have the factor for DW. For the permanent loads and also for the load, for the live load, we have different factors. So this process, defining the rating case, is for that. So let's look at the strength limit state, more visible with different factors. DC, maximum 1.25 can be applied and minimum 0.9 can be applied. But this is, you can think of it as a load combination. So for the DC load, DC group of load cases, 1.25 and 0.9 will be applied, and DC after 1.25 to 9 will be applied, and DW and so on. But then for DW type, you actually need to let the program know which one exactly is the DW load case. So this load type, it's literally only the load type. And it's now up to you to specify which load case is for different load type. So is this portion clear? It's also covered in the load rating tutorial, but a lot of people get confused with this portion. So you can simply think of it as like a load combination, but the defining things that are over here, this isn't the load cases. They are the types, so that we can designate specific vectors for that type. And 1, 2, 3, whatever the case be, one or multiple load cases can be DC after type, right? It's not just one single load case that will be DC, that will or likely to be DC after. So this one, let's say erection load 3 is also part of the DC after, the component load after composite load. So this is why, this is actually the way this interface works. And once you do it, you need to modify or edit. So yeah, please make sure for each load type, you actually specify which load case belongs to that load type. Yeah. One of the common mistakes, nothing over here, nothing over here, and nothing over here. And of course, the rating result wouldn't make sense, right? Because there's no loading data. Okay. So this part I really wanted to highlight on. The rest information, since we are exactly on time to finish, I'd like to conclude it over here. Due to the time constraint, I won't be able to collect the questions right now. So please feel free to let us know by email. And all the questions that were submitted already, I'll be answering them by email and also providing the materials for the training session today for all the attendees.